Well, so our last speaker of the day is Yi Li, who's going to talk to us on deep learned beamforming for Coherent Multi-Transducer Ultrasound System. Brilliant, over to you.
Well, hello everyone, my name is Yi Li. So my presentation is about deep learned beamforming for Coherent Multi-Transducer Ultrasound System. So I will call this Coherent Multi-Transducer Ultrasound System COMTUS in my following presentation. So first thing first, why do we need the COMTUS? So for the conventional ultrasound, the imaging performance is limited by the handheld transducer. So it do not have huge aperture size. And if we have the huge aperture size, the geometry cannot adjust patient's body very well. So for the COMTUS, we have multiple transducers which can have expanded aperture, so it can lead to improving imaging performance, and multiple transducers can fit patient's body better. Here is an ultrasound sequence. So we transmit on probe 1 and received by both, and we transmit on probe 2 received by both. We got 4 data sets here. We coherently combine 4 data sets. In this way, we got the increased signal-to-noise ratio, and we have extended field of view, and we can improve the lateral resolution. This slide is about beamforming. So in ultrasound, beamforming is quite vital because beamforming is about how the ultrasound system prepares the sound wave and how it processes the acquired signal. The beamforming can adjust the phase and amplitude of signals, and it can focus, steer, and oxidize the ultrasound waves. In this figure, I showed the beamforming in reception. So here you can see the elements received the signal from scatter, and the beamforming applied delay and optimization, and then we can get the beamformed RF data. So there, delay and sum. This is called delay and sum. So it's a widely used conventional and fundamental beamformer in ultrasound, and it also serves as a benchmark in this study. So COMTUS brings 3 challenges to beamformer. First one is flexible geometry and discontinuous aperture and large data volumes. And in this study, we will address the discontinuous aperture and large data volumes here. You can see this is an example. The discontinuous aperture can lead to extra artifacts here. For example, the side lobes. And if we have n transmissions in COMTUS, we will have n squared data sets for 2-probe COMTUS. So we need a deep neural network beamformer for the COMTUS to mitigate above challenges and exploit its aperture advantages. This is a pipeline of this study. So we create the phantom, then we use the simulation, field-to simulation, to have the raw RF data. This is the geometry of COMTUS in our simulation. So with the raw RF data, we apply perfect delays here. We got 4 data sets. In these 4 data sets, the COMTUS data sets, we have 576 channels. In conventional delay and sum beamformer, we just sum across these channels, and we apply some post-processing to get the final image. But we developed an expanded UNet here to get a B-mode image in linear scale. For visualization, we apply log compression to get a B-mode image in dB scale. Here, in this study, we also developed a post-reconstruction deep neural network. So it has the same, well, very similar structure as the physics-informed UNet, but the input channel is different. So here, it also applies the same post-processing as a physics-informed UNet. This slide shows how we made the phantom. So here, we take the real photographic image from the ImageNet, and we apply some pre-processing to have an amplitude map. With this amplitude map, we map the scatters in phantom to that amplitude map, so we get a phantom that looks very similar to amplitude map. In this way, we got the phantom, which can be used in simulation, and we bind every scatter in this phantom to the pixel it falls into, and we crop it into the field of view. In this way, we got the ground truth in this study. And this is configurations. So I want to emphasize that for the delay and sum beamformer, we have 15 plane waves from single transducer ultrasound, and we have in total 14 plane waves for contours delay and sum. But for the deep neural network beamformer, we only have 1 plane wave and 2 plane wave for contours. So we actually saved the acquisition energy and acquisition time. This is the first result. So it's mainly about the post-reconstruction deep neural network versus physics-informed deep neural network. We can see that the post-reconstruction deep neural network cannot really have clear backgrounds, and the physics-informed deep neural network can provide better contrast over this background and this anechoic inclusion, and the physics-informed deep neural network can provide less artifacts. For example, the edges here are clearer than the post-reconstruction model. And here, the physics-informed beamformer can also provide some speckle-like texture, because and this texture might be useful in clinical. Hence, only the physics-informed deep neural network are presented in my following presentation. This is actually the first result. So this is 2 unseen examples within the training domain. You can see that these 2 are deep neural network beamformer, and the left-hand side is single transducer, right-hand side is contours. We can see that the contours plus deep neural network beamformer can provide sharper edges among them, and it have less distortion, especially for some edges and for some shapes here. And it can provide better contrast. And this is 2 metrics for actually total 50 examples in my test datasets. So you can see the mean absolute error and structure similarity. They all shows that the contours plus deep neural network beamformer shows the best performance here. Next test is the cross-domain inclusions. So here, actually, this phantom have 4 inclusions. So anechoic inclusions, -6 dB, +6 dB, and hypoechoic inclusions. And here we can see that the final model, it produces less distortion. You can see the anechoic inclusions and hypoechoic inclusion is quite clear among them. And it can produce finer speckle. You can see this speckle is quite fine than the delay and sum beamformers, and it produce actually it produced some issue about scaling artifacts, especially at the around the hypoechoic inclusion. You can see there's some like scaling issue, but overall the last one, the COMTOS plus deep neural network beamformer performs best over them. These two examples is the point targets. So this is point targets, actually a grid of point targets in anechoic background and speckled background. So actually, you can see the deep neural network beamformer can produce clearer backgrounds than the delay and sum beamformers, and we will focus on these two examples, which is COMTOS plus delay and sum beamformer and COMTOS plus the deep neural network beamformer. We will see the profile of central point. Okay, you can see here, the green one is deep neural network beamformer. The orange one is delay and sum beamformer. So you can see the deep neural network beamformer can sharpen the main lobe and it can effectively suppress the side lobes here. So and you can see among the backgrounds, the deep neural network can produce clearer backgrounds. And this is the FWHM of total 15 point targets. So you can see, firstly, COMTOS data sets, which is this one, and this one, and this one. They all they all perform better in speckle background than the single transducer case. So we can see that COMTOS provides extra robustness on speckled background. And we can conclude that the COMTOS plus deep neural network, these data sets and this data set performs overall better among them. These results are two in vitro tests. Okay. This is an in vitro test, so it's from experiment. So it's not perfectly delayed. And we can see that deep neural network can reduce the artifacts, especially the side lobes here, and it can produce the better contrast in inclusions and the points there. So conclusions. Firstly, the physics-informed deep neural network outperforms the post-reconstruction deep neural network, but the difference of the structure is quite tiny, just the input channel. And secondly, COMTOS large aperture improves the sensitivity, resolution, and field of view, and it provides extra robustness on speckled backgrounds. But the discontinuous aperture introduces extra artifacts, provide more like challenges for conventional beamforming. Thirdly, deep neural network outperforms the delay and sum even with 1 or 2 plane waves versus 15 or 14 plane waves. It can reduce the acquisition time and energy. Finally, the COMTOS plus deep neural network performs best overall. So it indicates that deep neural network can really mitigate COMTOS challenges and exploit its aperture advantages. Yeah, that's all. Thank you.